The particular example of the parabolic partial differential equation we are going to consider here is going to be the heat or the diffusion equation. So let's first present the equation here. This is the equation. As you can see, it's second order time spatial derivative and first order time derivative. And it's connected in the simplest version of this heat diffusion equation. This d will be just a constant, but in general, of course, it could be any function of x and time. And as always, all the equations are based on some principle that we have to apply in order to derive that equation. Here, as it's based on some physical principle, but it's completely natural in the sense that the principle that we are applying here, just for curiosity, even though it's here in this case, it's not so important, we are applying the conservation of heat energy inside a volume game, and therefore we have that the change in the energy here inside, so the change in the temperature inside this volume, is equal to the flux of heat. So the heat that enters and the heat that goes away. So the balance between these two fluxes, that within the Fourier law is proportional to the gradient of temperature when the changes in temperature from the inside the volume to outside the volume is high, then the flux will be higher. And besides that, it will be also proportional to these constants that it's called conductivity. But this is not important at all. We just have to center on these equations. We are given that equation and we have to analyze that numerically and try to find finite difference representations for this equation. So, however, I think it's important in order to have developed intuition for that kind of equations, and in this case, this kind of parabolic equations, it's important to have what's the type of the solutions that, how the solution looks like in this case. And actually, let's consider, for example, and we are plotting here the, let's suppose that this is like initial condition. So that would be like the initial condition. We are writing that to be like some function which just depends on x, and we are calling that function u0, which is the initial condition. It could be like a temperature on a wire as a function of x, for example. Then the solution at another time t it looks like something similar to this one. It would be something like that. So basically what happens is in the diffusive equation, you have that the peaks get smoother. So that happens basically is that as talking about temperature, the temperature will be decreased at such points where the temperature is a maximum. However, on the sides where the temperature is smaller, you have the temperature increases. Basically, the heat and the energy, which is concentrated initially here, diffuses and goes to the side. That's why we have the profile will be like much smoother function. And not only intuitively or qualitatively, as we are showing here, we can also have the analytical solution for that equation. Of course, just in the case of the d constant of the d parameter in the equation to be constant. And the general solution for the diffusion equation with arbitrary conditions, which basically means that this is the initial condition, as we have said before, some function, we are going to call it u0 depending on x, and with free boundary conditions, which means that the derivative on the sides, on both sides, on minus infinite or and at plus infinite is going to be 0. Then you have that the general solution can be written in this way, which basically we have the following: the u function at point x at any time t is 1/2 square root of pi. D is this parameter, the conductivity, which arises in the equation, times t, and that's the integral from minus infinite to infinite. This is the function that we have initially. In this case, we have the integration parameter, we're calling it s, and then we have an exponential minus x minus s to the square over 4 times d times t. So that's the interval that we need to solve in order to have the explicit solution for U once we have the initial condition, this one. I think this kind of solution is interesting whenever we can apply it so that we can compare that with a numerical method. At the same time, it's also important to have the qualitative picture of the solution so that we know more or less what kind of solution that we should expect whenever we apply a numerical method. And that's interesting in order to check, in order to have the first idea if the implementation of the method is going the right direction or it's going in the wrong direction.